When you started looking at laser cooling the cesium atoms, what was already kind of like, what were you building on? So what
Yeah.
had already been done?
Well, so we didn't do cesium atoms first because we didn't have the lasers. We only had lasers that could do sodium.
Okay.
So we started with sodium. We figured, you got to start somewhere. And, at the beginning, we were thinking, let's develop the ideas of laser cooling. And then once we've got the ideas developed, then we'll think about how to make the clock. The fact of the matter was, we weren't really thinking ahead that far. We were just thinking, it's going to be cool to laser cool these atoms. And once we got them laser cooled, we'll worry about the rest of the thing. I really think that if we had been foresighted, if we had thought, let's figure the whole thing out, what kind of clocks we're going to make using these laser cooled atoms, we would have given up right at the start. Because the understanding of laser cooling at that time put a certain limit on how cold you could get the atoms. If the atoms had only been that cold, they really wouldn't have made a very good clock. But we didn't worry about that. We just said, hey, it's got to be good. And we accidentally discovered that we can make the atoms hugely colder than what the theory said was possible. In the end, we got cesium atoms 200 times closer to absolute zero than what was predicted by the theory. And if we were stuck with the old, what we now call the Doppler cooling limit, it wouldn't have made a very good clock. But with the cooling limit that we got because of the accidental discovery of sub-Doppler laser cooling, with that, we make damn good clocks. And today, most of the industrialized countries of the world are using cesium clocks to keep time, connecting to the rest of the world through these various means, and basically keeping time for the whole world. So UTC, Universal Coordinated Time, is determined mainly by laser-cooled atomic fountain clocks using the techniques that our research group developed and other research groups developed.
So what made you to contest the Doppler limit?
Well, we didn't contest the Doppler limit. We accidentally discovered that it wasn't right. So here's the story. So when we finally got laser-cooled atoms down something close to the limit in what we called optical molasses. So the idea is we're bringing laser beams in from different coordinate axes so that we're cooling the atoms along all three spatial dimensions. And Steve Chu was the first to do that at Bell Labs in 1985, measured the temperature. And he developed a technique that we now call release and recapture. The idea is you got the laser beams coming in, cooling the atoms. Now you suddenly turn the laser beams off. Now remember, this is all in a vacuum. So you suddenly turn the laser beams off. So now what's going to happen? Well, those atoms are going to fly apart because they've got whatever thermal velocities they have. They were also using sodium for the same reason we were, that sodium was the only atom that we had the lasers to.
And what were the lasers?
The lasers were dye lasers. That we were still
what
using.
was the wavelength?
Well, the wavelength for sodium, it's the wavelength you see in these beautiful sodium street lamps, 589 nanometers.
Mm-hmm.
So that's a nice sort of orangey yellow.
So you use like sodium kind of based lasers for pumping the sodium?
Yeah, for doing the laser cooling.
I see.
And they were stabilized to about 1 megahertz, maybe a little bit better. That was fine because the line width of the sodium optical transition is about 10 megahertz, so the lasers are well under that. Well, anyway, they measured the temperature by having the atoms just turn off the laser beams, so the atoms are jiggling around, not getting very far because the lasers are damping their motion so strongly. This is where the name molasses comes from, that the atoms feel like they're in a viscous fluid and they can't get out. It takes them a second to get out, whereas it would take them milliseconds to get out if they would just move unimpeded at their really cold temperatures. But it's instead they stay around for a long time. And then you turn the laser beams off. Now the atoms, okay, they just expand at whatever velocities they have. And then you just turn laser beams back on after a few milliseconds, and that's the recapture part. So you turn them off, that's the release part. You turn them back on, that's the recapture. And by looking at the ratio of how many atoms are left when you turn it back on to how many atoms you started with, and knowing all the geometry.
How do you count them? Is it fluorescence? Or?
We don't count them, we just look at how bright the amount of atoms is by looking at the total fluorescence. And so from that, you can calculate what the temperature is, but you have to know what the geometry is very well. So there's a big uncertainty. So they reported what the temperature was. Now, the theory said the coldest you can get is 240 microkelvin. Now, that's really, really cold, okay? Because room temperature is about 300 Kelvin, okay? And we're talking about getting the temperature down to 240 microkelvin. Okay, dilution refrigerators, sort of the coldest thing that people do when they're doing condensed matter physics. Typically, you get to 10 millikelvin. Okay, if you use adiabatic demagnetization, you can get down to the microkelvins, but it's tough. And here, you're supposed to get down to 240 microkelvin. Fantastic. And so Steve Chu measured it with his colleagues, Art Ashkin and John Bjorkholm, whatever. Alex Cable, what a guy. Alex Cable, I'm pretty sure he was on that paper. He was sort of a technician for Steve Chu. At some point, Steve was encouraging him to go to graduate school because he's a really smart guy, really could do all kinds of great stuff in the lab. But he decided instead to form his own company.